on that note, it's time to finally get into the nuts and the bolts of the Riemann zeta function. I believe we have restored swiveling capabilities. Yes, OK, just with a 1 second delay. OK, that's not so bad. So I'm going to mix things up a little bit. There are lots of different ways to attack the Riemann zeta function. We've stated what the definition is. For what values of s does the Riemann zeta function make sense? So zeta of s was the sum, n goes from 1 to infinity, 1 over n to the s. It was the product p prime, 1 minus 1 over p to the s inverse. So for what values of s does this make sense? Real s is greater than 1. So unfortunately, if the real part of s is less than 1, this no longer makes sense. So we need a way to extend this. And so for some problems, it's enough to just extend it to the real part of s maybe is greater than 0. For other things, we want to be able to send the real part of s all the way off to minus infinity. And the idea is to do contour integration. So the question is, how much complex analysis do you guys want to see in this class? So far, no one has emailed me about seeing it, so I will not plan on doing much complex analysis. If that changes, either email me directly, anonymously. If you want to try Elvish, that's fine. I can try to translate that in the spirit of what we were doing before class. And I'm happy to go through some of the proofs of complex analysis as a way to try to motivate why you might want to take the course, how powerful complex analysis is. If not, you can just skim the stuff in the book. So what I'm going to do is, before we do the real proof of analytic continuation of the Riemann zeta function, let's do the cheap versions. So cheap analytic continuation. So sometimes I think they call it zeta star of s, also eta of s for the Dirichlet eta function. So Dirichlet eta function. And this is the sum, n goes from 1 to infinity, of negative 1 to the n minus 1 over n to the s. So it's 1 minus 1 over 2 to the s plus 1 over 3 to the s minus dot, 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 dot. What's nice about this function? Everywhere? A lot of places. Yeah. I mean, cover your ass. Okay, don't go. It converges everywhere. That's too bold of a statement. So give me a value of s where it's not going to converge. 0. Give me another value of s where it's not going to converge. No, 1 is awesome. It's going to converge at 1. For an M&M, what does it converge to when s equals 1? So you get 1 minus a half plus a third minus a fourth plus a fifth.
Oh, ln of 1 minus of 1. No, not 1.
You're close.
Ln of 1 half.
So ln of a half is negative. Ln of 2. All right, so this was a good team effort. You can all get M&Ms. All right, ln of 2. So why? Well, the natural log of 1 minus x is the sum. N goes from 1 to infinity of x to the, oh, I'm sorry, we want 1 plus, of negative 1 to the n plus 1 x to the n over n. And when you have something like this, you can write it either as n plus 1 or n minus 1. If I'm calling that n minus 1, all right, I'll write it as n minus 1. It's only going to change the exponent by parity. Doesn't really affect things. So this is the natural log of 2. This is really nice. So as long as the real part of s is greater than 0, we're OK. Why does this belong on the same board as the Riemann zeta function? Is it that different? It's an alternating version of the Riemann zeta function. And so all we've done is we've changed the coefficients from being 1 every place to being -1 to the n minus 1, to just alternate. And in fact, if you look at this, this is the beginning of an introduction to generalizations of the Riemann zeta function to L functions. When can we put something in here that's interesting? And it turns out that zeta star of s, let me just make sure I do it the right way, is going to be 1 minus 2 to the 1 minus s times zeta of s, or zeta of s is 1 minus 2 to the 1 minus s inverse zeta star of s. If you think about what's going on, I take the zeta function, and at the evens I don't. At the evens, I have to change the sign to be negative. At the odds, I don't do anything. So if I multiply by a power of 2, what I'm doing is, if I now have the zeta function, if I multiply by powers of 2, I take all the n's in the denominator, and I now replace them with twice that value. So if I have 1 over 5 to the s, I'll get 1 over 10 to the s. The extra 2 up top means now that when I subtract it, I started off with a 1 over 10 to the s with the zeta function. I subtract off 2 divided by 10 to the s. I'm left with a -1 over 10 to the s. So that's why I have something like this. I should really view the 2 to the 1 minus s as a 2 divided by 2 to the s. And this is something that I really obsess about, the right way to view algebra. The right way to view the 2 to the 1 minus s is I'm multiplying by 2, and then this 2 to the s is going to combine with the stuff down here. And now I'm just going to have all the even numbers. And then since I'm subtracting them from here, wherever I had a positive even number, I'm now going to have a negative. And it turns out that this series converges for all values of s where the real part of s is greater than 0. So this gives an analytic continuation to the Riemann zeta function. So I won't go through all the details. What would be the most interesting value of s to take?
0. Not greater than 0.
Yeah, we're not allowed to do s equals 0. Where would be an interesting value of s to take?
Very small numbers close to 0.
Okay, small numbers close to 0. But nope. So I have the original zeta function. What's the first place where the Riemann zeta function goes? Where do things break down? 1. Let's take s equals 1. Well, if I take s equals 1, the zeta function's blowing up. This is well defined. I've got 1 minus 2 over 2. Oh, great, that's 0. What's infinity times 0?
0.
Depends, what do you want it to be? Right? No, there's lots of different things. One of my favorite examples, I'll do this as an aside. Do you know that infinity times 0 is -1?
I did not know that.
No. So let's take two lines that are perpendicular. What's the product of the slopes of two lines that are perpendicular? Product of the slopes is -1. -1, -1, -1, -1, -1. 0 times infinity. So 0 times infinity is -1.
In a different basis.
So depending on the problem you're looking at, 0 times infinity can be anything. For this particular problem here, it's going to be -1. For the Riemann zeta function, it's going to be something else. And so we can actually use this to try to figure out what's going on to the zeta function. So we've got, zeta of s is 1 minus 2 to the 1 minus s inverse zeta star of s. As s goes to 1 from above, what does zeta star of s go to? ln of 2. And I just realized, I had no sleep because too many of you were emailing me late at night. I should not be writing ln of 2 in an advanced math class, but you got me. I'll do ln of 2. What do you think that goes to?
It's just a random question. Why don't people use ln in advanced math classes?
Because the only base you care about is
Yeah, I was going to say, you're going to work base 5? Going to work base 10? Base E. It's the only choice. Okay? There's no other choice. Because otherwise, when you differentiate, you have to remember, crap, I've got b to the x. When I differentiate, do I bring down a natural log of b? Do I divide by natural log of b? Which way do things go? If you do things with base e, things are much nicer. So we always do things like that. I can't prove that the universe doesn't care that we have 10 fingers, but I'm highly suspicious of anybody who claims that the universe cares that we have 10 fingers. Now, base 2, however, that is natural. And there are some problems in number theory where base 2 does make an appearance. Base 3 occasionally makes an appearance, but for the most part we do base e, and so we just adopt in higher mathematics that log means base e. It also allows us to confuse the lower people. Oh, I wasn't supposed to reveal that. So now we want to understand what's going on here. How should we figure out what's going on here?
S is really big, then...
Well, S is not really big. S is going towards 1.
Well, as S gets smaller
Okay.
from being really big, 2 to the 1 minus S approaches 0.
It approaches 2 to the 0,
2 to 0
which is?
1.
So we want to understand this. So to understand this, we have 1 minus e to the 1 minus s log 2. This is very similar to it's similar to what? Whenever you have a product,
Something we can take the...
it should be instinctive now. I'll try to find that cowbell. Take logarithms. And this goes back to the question you were just asking a moment ago. Why do we do everything base e? Do you know what 1 minus e to the blah looks like? Do you know how to understand e to the u, e to the x? Yeah. We know e to the z is 1 plus z squared over 2 factorial. Do you know what 2 to the z looks like? You've got to worry about where do you put those log 2's and everything. Well, it's going to come in right here. So this is going to become 1 minus, and then e to this is 1 plus 1 minus s log of 2 plus 1 minus s squared log squared of 2 over 2 factorial. And then I have to remember I've now switched notation. I just can't do it anymore. Log 2. So when I expand this out, the 1 minus 1, that cancels. I've now got 1 minus s with a negative sign, so that becomes an s minus 1. So I get, oh, and this whole thing is supposed to be the negative 1 power. Phew, good. So I get s minus 1 times log 2 plus big O of something of size s minus 1 squared inverse times the natural log of 2. So what this means is this looks like the log of 2's cancel, because remember this is inverted, and this looks like 1 over s minus 1 plus small. And this tells us that as s approaches 1, the Riemann zeta function looks like 1 over s minus 1. If you haven't had much experience with this, if you want, I'll show you how to get the next lower order term. Do people want to see the algebra for that? Okay. Okay. So let's see if we can make a slide. Okay. So what we really have is we have s minus 1 log 2 plus s minus 1 squared log squared 2 over 2 plus dot dot dot. And we have log 2 up top. I'm not going to worry about the other stuff. Okay? I'm going to show you how you would do calculations like this. Let's pull out an s minus 1 log 2 from everything. We'll have a log 2 divided by s minus 1 log 2. And now we're left with 1 over 1 plus s minus 1 log 2 over 2 plus dot dot dot. And now we can expand this using, how would we expand that? So is everybody comfortable as to how we got here? I just pulled out the s minus 1, because when s is really close to 1, the main term is the first term. This is extremely small. This is most of the contribution. So let's pull out, and I can write the denominator as 1 plus something small. I'd use the geometric series formula. And so when I expand this using the geometric series formula, the log 2's cancel, and I get 1 over s minus 1, and I get 1. Now, I've got to write the plus sign as a 1 minus negative, right? And so I would get minus s minus 1 log 2 over 2 plus yada, yada, yada. Then I would have the squared term and so on. The s minus 1 cancels one of the s minus 1's over here, and I get 1 over s minus 1 minus, if I've done everything correctly, log 2 over 2 plus yada, yada, yada. And everything else is going to be smaller.
Would we be allowed to just originally use that like 2 to the u as continuous and then just say that 1 minus s gets close to 0 as s goes to 1, so then that gets arbitrarily close to 1?
That this gets arbitrarily close to 1?
Yeah.
Yes, we can use that it gets arbitrarily close to 1. But we need to show that.
And then that gets arbitrarily close to 0. And then that gets arbitrarily close to infinity.
But we need to know how quickly.
Okay.
And that's the problem. So we talk about the order of a 0, the order of a pole. If I give you the function f of x is x to the 5th plus 12x to the 6th, it starts off as x to the 5th. It has 5 zeros at the origin. If I give you the function that's 13x to the 5th plus x to the 6th, it's still 5 zeros at the origin. If I give you 1 over x, we say it has a pole of order 1. If I give you 1 over x squared, it's a pole of order 2. Because I have a 1 over s minus 1, this is a pole of order 1. We want to know, is it a pole of order 1, order 2, order 3? It's very important that it's a 1 over s minus 1. This is a hell of a lot to get out of just looking at the alternating zeta function. We get an analytic continuation of the Riemann zeta function, and we get an idea of how it is blowing up at the origin. And if we wanted to, we could isolate out the next term here. It gets more involved the more you have, because we have to keep in track all the stuff when we're doing the geometric series expansion. That's going to become painful. But we can get up to the first correction term, I think, without too much trouble. So this is a common technique in terms of how you handle stuff like this. You want to try to figure out what is the pole, what is the residue, what is the multiple of it. So it's 1 over s minus 1. So as s goes to 1, it blows up. It blows up like 1 over s minus 1. We say it has a pole of order 1 at s equals 1 with a residue of 1. Right? So that's the big thing that we can deduce about the Riemann zeta function here. Okay. Any other questions about the alternating zeta function? Yes?
So that is our second, the log 2 over 2 is our second order error term?
Well, I wouldn't really call it an error term. I would say maybe it's the expansion. We're trying to understand what does this function look like near s equals 1. I may have made a small algebra mistake here. I wasn't planning on doing this. I am quite happy to have this class. I prefer to have this class actually adjusting content based on what you guys want to see. And so I know enough number theory that I should be able to do most of this on my feet. And I'm happy to go through this. I have not checked to make sure that this is correct. There could be an algebra mistake. Knowing me, good chance there's an algebra mistake.
I was just wondering if there should be an s in...
No, because this is the constant term.
Okay.
This is the one. This is the s minus 1 to the negative 1 term. This is the s minus 1 to the 0.
Right.
And the next one will be s minus 1 to the first. To get the s minus 1 to the first, I have to take the piece from here, and then I have to take the squared piece here. And then the first part of that, when I multiply by 1 over s minus 1, will also give me an s minus 1 piece. Okay. Any other questions on this? So this is the first way to get analytic continuations of the Riemann zeta function. I'm not going to go through the details. It's in the book. I just want to state another way to get an analytic continuation, and then we'll go into the way that I really care about. So the next one is, let me just write it correctly. Zeta of s is s over s minus 1 minus s times the integral from 1 to infinity of the fractional part of x. So this means x minus the floor of x times x to the negative s minus 1 dx. And it turns out, see page 61, this is going to come from looking at the sum of 1 over n to the s is going to be a sum, and it goes from 1 to infinity, n times 1 over n to the s minus 1 over, I think it's n plus 1. Yes. Okay. So if we look at something like this, what kind of series is this? Can you tell what kind of series this is? It's telescoping. It's not completely telescoping. If it was completely telescoping, we would only have the first and the last term. It's mostly telescoping. Yes?
Sorry, I can't. What is that at the very left say?
This?
Yeah.
Page 61.
Oh, okay.
So I feel like Princess Bride. It's mostly telescoping. Okay? And because it's mostly telescoping, you actually get something interesting. What you're getting is the Riemann zeta function. And now when you see something like this, what does this remind you of? This is an integral. And we're evaluating the integral at 2 points. And now, the n over here, you can look at that, if you want, as like x minus the fractional part of x. And if I look at x minus the fractional part of x, that's constant on an interval, from 5 to 6, 7 to 8. And so, again, I'm not going to go through the details of this. The details of this are in the book. This is another way to get an analytic continuation of the Riemann zeta function. What's nice about this is you have a nice integral representation. You can also see that it blows up when s equals 1. Now, I've written things a little bit differently. I've got an s over s minus 1. You can play games to figure out exactly what that should be. One thing you could do is you could write s minus 1 as s minus 1 plus 1 if you want. And if you write it like that, then the piece is going to become 1 plus 1 over s minus 1. And again, you can see the 1 over s minus 1 coming out. So when I wrote it as s over s minus 1, as s goes to 1, it's still looking like a 1 over s minus 1. There's this little shift of plus 1, but in terms of the size of the function, if you're infinitely large and I add 1 to you, I really have not changed your value. Now let's look at this integral. What can you tell me about the fractional part of x? What do you know about it? So what's going to be true about the fractional part of x?
Periodic.
It's periodic. What else? Less than 1. Well, yes, technically it is. The way it's defined, it is technically less than 1. I would have said less than or equal to 1 to just cover myself, but yes, less than 1 works. So it's strictly between 0 and 1. So when I'm trying to evaluate how big is that integral, if I want to get a sense of what kind of contributions am I talking about, well, what would I get? If I look at what's going on, I have the integral from 1 to infinity, the fractional part of x to the negative s minus 1 dx. Let's write s as sigma plus it. If we take absolute values, so the absolute value will be less than or equal to the integral from 1 to infinity of 1 times x to the negative sigma minus 1 dx. And the reason is, when I look at x to the it, the absolute value of x to the it is 1. X to the it is e to the it log x. And that's going to just be 1.
So for sigma greater than 0, that's going to...
So now this converges for sigma greater than 0. So beforehand, if we had x to the negative sigma, we need sigma to be greater than 1. But now because we have a negative 1 there, this is great. This works for even more. This is okay if sigma is greater than 1. I'm sorry, greater than 0. And so this gives us an analytic continuation of the Riemann zeta function. And it now makes sense as long as sigma is greater than 0. So the way you should look at it is here's 0, here's 1/2. That's going to be very important in the rest of our lives. Here's 1. Initially, we know things about the Riemann zeta function over here, where the real part of s is greater than 1. To be able to understand and use the Riemann zeta function to attack questions about primes, we want to know the Riemann zeta function for other values of s, for s going all the way off to minus infinity. So one approach is the baby step approach. You say, well, let's just first extend it so it makes sense going all the way down to 0. And so we have two different proofs that allow us to extend it all the way to here. And so now we understand the function in that regime. Does this mean if I put in s equals 0, that 1 plus 1 plus 1 plus 1 plus 1 is a reasonable thing to look at? No, it no longer means the sum of that. This is why you get the absurdities when you put in s equals -1, that the sum of all the positive integers is -1/12. Okay? I do not believe the sum of all the positive integers is -1/12. No matter how little sleep I have, that's not going to, I hope I will not ever utter that. What I will utter is that this function agrees with the sum of 1 over n to the s if the real part of s is greater than 1. And this function can be continued in such a way that it makes sense for other values of s. And for those continuations, it turns out that there's an interpretation. If you want, you can interpret this as this is what we mean by the sum of the positive integers. But we're not saying that this is what the positive integers sum to. Okay, so the next question is, do we have a better way to analytically continue this? Can we continue this not just to the real part of s greater than 0, but to any value of s? Right now we know that there's a pole of the function here. So pole, so it's a simple pole, and the simple just means it looks like 1 over s minus 1 at s equals 1 of residue 1. So that means it looks like 1 over s minus 1 plus something nice as s goes to 1. So we have some information. The question is then, where are the other zeros in the poles of the Riemann zeta function? The prime number theorem turns out to be equivalent to the fact that the Riemann zeta function is not 0 on the line real part of s equals 1. You had a homework problem which was to prove the Riemann zeta function is non-zero for the real part of s strictly greater than 1. So if you take your homework problem and you take zeta of s does not equal 0 if the real part of s is greater than 0, if you just add one diagonal slash line like this, you have the prime number theorem. That's all you need for the prime number theorem. It's a bit of work to add that. Okay? There's probably not going to be time to do that today, so we'll probably save that to Monday. I'll go through Merton's argument. It was not the first proof that the Riemann zeta function is not 0 on the line of real part of s equals 1, but it's the slickest, it's the nicest one I know, and it uses one of the greatest inequalities in all of mathematics. So if x is a real number, what can you say about x?
X squared.
All right. So this fails violently for complex numbers, primarily because you can't even order complex numbers. But for real numbers, if you take any real number, its square is non-negative. This is one of the biggest tools we have in the game. And that's why I want to go through Merton's proof. Merton's proof is not as difficult as a lot of the other things we're going to be looking at this semester. But it's such an important idea that it's worth, it makes the cut. So what we want to do is we want to talk a little bit more about continuing the Riemann zeta function. For now, I'm not planning on going into too much detail about analytically continuing the gamma function. I will think a little bit more about if I want to go into a little bit more detail on that. I know some of you have already seen it. The analytic continuation of the gamma function is not too bad. And I wanted to concentrate on the analytic continuation of the zeta function. there is a connection to Benford's law, and as s is getting closer and closer to 0, you're getting very close to the Benford density. The Benford density is 1 over x. And so there is a Benfordness going on. And in fact, I didn't realize it at the time, but my first introduction to Benford's law was when I was reading Sears' A Course in Arithmetic. And he talks about analytic density versus arithmetic or natural density. And there's an aside where he says Bombieri has shown that the analytic density of primes that have first digit 2 is, that have first digit 1 is the log of 2 base 10, which is the Benford probability. And so it's just this passing remark. Sears' book does not say Benford's law in it at all. He's not really concerned about thinking about Benford, but it is a Benford stuff. And so there is a nice connection. Maybe we'll talk a little bit more about that. But at this point, I'm trying to be very careful as I erase. Let's get rid of the cheap analytic continuation. And we'll go to the Deluxe. All right. This, yes.
I just have one quick question. So we have said that there's a simple pole at s equals 1.
Yes.
Why don't we try to find an analytic continuation so that there's no pole there?
Because there is a pole.
But there's no then a pole everywhere to the left also because it will
No.
go to infinity?
No, because the function looks like 1 over s minus 1 there. So if I multiply my function by s minus 1, that will get rid of the pole. So for instance, if I just look at s minus 1 times zeta of s, and now I take the limit as s goes to 1, this now equals 1. And I've gotten rid of the pole. And so what's nice is that if you have a pole, it does not screw you for the rest of eternity. It only screws you locally. The interesting thing in complex analysis is it's those troublesome points that make life doable. It's the points where the action happens. What makes things so difficult is we have to work with the complex logarithm. And so, just as an aside, function derivative. X squared goes to, x goes to, 1 goes to, x to the minus 1 goes to, what does it go to? No. Negative x to the negative 2. Look, this is to the first power to the 0th power to the negative 2 power. There's something missing. If I do x to the negative 2, this goes to negative 2 x to the negative 3. The powers are decreasing by 1. Something is wrong here. I don't have a 1 over x. What function gives me a derivative of 1 over x? It's the natural logarithm. In complex analysis, the natural logarithm has an enormous role in terms of describing what happens. And it comes down to over here on this side, the 1 over x, when you try to go backwards, what did it come from? It's not a nice function like this. All right, so let's do the Deluxe continuation. We've got about 12 minutes. That should be enough time. So I have written it here so I don't forget. So we're going to define zeta of s. Well, I'll use c of s. This is the completed Riemann zeta function. This is going to be pi halves to the negative s halves, s times s minus 1, gamma of s halves, zeta of s, where gamma of s is equal to the integral from 0 to infinity of x to the, I'll do it this way, of e to the negative x, x to the s minus 1 dx. The gamma function has lots of nice properties. Gamma of s plus 1 is s gamma of s if I've done it correctly. And this is the functional equation of the gamma function. It allows you to take the value of the gamma function in some regions and extend it to others. The s minus 1 over here, this is going to cancel the pole of the Riemann zeta function. And the theorem is that c of s is c of 1 minus s. So I can understand all of this stuff over here when the real part of s is greater than 1. And this is going to allow me to then understand things in other regimes. Okay, so now the question is, how do we go about proving something like this? So again, I don't want to go through all the algebra. I want to just try to go through the key ideas. And so there's several different ways to do the proof. I'm going to start off by stating a function which I think is important, and then we will describe some of the consequences of this function. We're at the point where it doesn't want to turn anymore, so let's see if it, there we go. Thank you for waking up. Okay, so let's set omega of x is going to be the sum, and it goes from 1 to infinity, of e to the negative pi n squared x. Theta of x is going to be the sum, and goes from minus infinity to infinity, of omega of x. Whoa, not omega of x, sorry. E to the negative pi n squared x. How can you relate that to omega of x? Yes?
Twice it, and something plus 0,
Plus 1. So this is coming from the n equals 0 term, and this is coming from the n greater than 0 and the n less than 0 terms. Right? So if I understand omega of x, I understand theta of x. If I understand theta of x, I understand omega of x. Which do you like better? Great. Why do you like theta better? Poisson summation. So Poisson summation says, and I think the way I've written it is, theta of x is x to the, I think, minus a half theta of x to the minus 1. So this is the functional equation for the theta function. It relates its value at x to its value at 1 over x. So relates values between x and x inverse. If I understand how theta transforms, do I understand how omega transforms? Yes, it's roll up sleeves, do algebra, right? There's no more thinking that has to be done. There's no new Poisson summation that has to be done. I know how theta transforms. I can solve for omega in terms of theta. So this gives me a relation for omega. Yields relation for omega of x. In an ideal world, when we have 20 hours a week to meet, and you get to do every single algebraic step, you go crazy. But in such a world, I would then go through all the algebraic steps. I'm not going to do that. It's in the book. You can read it. There is a simple way to get from theta to omega. The question is, why do we want to do something like this? And the reason we like to do stuff like this is when we have integrals from 0 to infinity, it turns out it's often really nice to write them as integrals from 0 to 1 and then integrals from 1 to infinity. And when we have an integral from 0 to 1, we'll change variables. We'll send x to x inverse, and then that would send the integral from 0 to 1 to an integral from 1 to infinity. And then this allows us to combine and have the integration over the same regime. That's what's going on. That's why we care. That's why we want to do all of this stuff. It's going to allow us to combine things in a very nice manner. Okay? Well, I mean, if I have a negative, I can always just play some games. I'm going to send x to x inverse.
If 0 goes to 0 inverse, the bottom bound be infinity.
Well, but I can then just multiply by negative 1 inside. I'm not going to worry about if I'm integrating from infinity to 1 or 1 to infinity. I can always flip that with a minus sign. Essentially, this integration is now the same as integrating from 1 to infinity. I can put these two things in the same regime. And I can try to stay away from values that are bad. Okay. Any questions about this part? All right, so now if we come back over here, so I'm going to, here is my definition of the gamma function. And so the inspiration is to look at gamma of s halves divided by n to the s pi to the s halves. And if we look at that, that's going to be the integral from 0 to infinity of x to the 1/2 s minus 1 e to the negative n squared pi of x dx. So this is the part that's not immediately clear as to why you would want to look at this. For a fixed value of s, is gamma to the s halves bad? Is gamma to the s halves bad if I fix s?
It's definite.
It's definite. It's some number. The gamma function generalizes the factorial function. It's just something. Pi to the s halves, again, pi to the s halves I understand really well. This stuff over here is just to make some of my change of variables look nice. The 1 over n to the s, that's the interesting piece. If you listen really closely, the fat lady is screaming at you to do something. Right? What is she screaming? She already screamed something about baseball last night. She did not scream until nearly too late in the Patriots-Jets games. What should you be doing over here? What should we do to this? Not simplify. That would be Thoreau. Thoreau is not a fat lady. I don't have time to prove that. What should we do here? What are we trying to study? The zeta function. What should we do? Sum over n. Isn't this, can't you see it's screaming at you to sum over n? Right? If you sum this all over n, this part over here is going to look like the zeta function. If we sum over n, what does this become? Omega. And so the reason we put the gamma function here is that gave us a nice representation of the 1 over n to the s. And now when I sum over all n, I have something here that's really nice. I have the omega of x. Okay? So there were two key steps here. The first was that we could express it, and so maybe I'll do it in 2 lines. So I'll go back. And so if I go like this, we have e to the negative pi n squared x. And now if we sum over n, we get pi to the negative s halves, gamma of s halves, zeta of s is equal to the integral from 0 to infinity of x to the 1/2 s minus 1 omega of x dx. So this representation, we're using the fact that we have an integral representation of the gamma function to write this in a very nice way, so that now when we sum over all n, we're in great shape. So really, we've put the n inside the exponent over here. Well, when you're doing the definition of the gamma function, I have e to the negative x. I need to do a change of variables. Replace negative pi n squared x with, say, u. And if I replace that with u, then over here you see you're going to have n squareds coming in. You've got a 1/2. And after you do the algebra, it is going to get you exactly what you claim over here. So you should go through, you should do the algebra. Yes?
So why are we getting an e to the negative pi n squared x? Because we only have gamma of s over 2.
Just when you go through and you do the change of variables. When you do the algebra at the end of the day, it turns out these are the same. If I want to evaluate this, I've got the 1/2 over here. And so when I change things around, I've got to have an s halves coming in because I have x to the s halves. But when I change my variables, if I call u pi n squared x, I'm going to be getting pi to like the 1/2 s minus 1 and all that stuff over there. So now the rest of the proof just proceeds exactly along these lines. And so based on the fact that we have 2 minutes left, doesn't seem to want to, there we go, it now wants to swivel again. We now just take this argument and we do exactly what was suggested. So we have pi to the minus s halves, gamma of s halves, zeta of s is equal to the integral from 0 to 1, x to the 1/2 s minus 1 omega of x dx plus the integral from 1 to infinity of x to the 1/2 s minus 1 omega of x dx. Now we take this integral over here, and we replace the integral from 0 to 1 with an integral from 1 to infinity by replacing x with 1 over x. And when the dust settles after we do the algebra, we end up getting that it equals the integral from 1 to infinity of x to the 1/2 s minus 1 plus x to the negative 1/2 s minus 1 omega of x dx plus 1 over s minus 1. So this is now just doing simple algebra. And so when we do the simple algebra, this is now what we get. And this makes sense, that we should be getting something like this. I'm replacing x with 1 over x over here. I'm then using the functional equation of the omega function, which relates its values at the reciprocals to the values of the original. There'll be some kind of shift with the x coming in. Oh crap, I've got this plus 1. That's probably where this part over here is coming from. So just getting a sense of where the pieces are coming from by looking at the expressions we have. This should be coming from the 1. The thing's going to be shifted a little bit. What can you say about this omega function? As s goes to infinity, as x goes to infinity, what can you say about the omega function? What's true about the omega function? No, you gotta use stronger words than small. 0, damn small, insignificant, right? Look at what's going on. You have e to the negative pi n squared. This is smaller than a geometric series. If I drop the square, it's a geometric series. Essentially, it's given by the first term. It's looking like e to the negative pi nx. When x is large, this is decaying exponentially. How fast are these growing? What's the growth rate for these? What's the word? Power polynomial. Or if it's, these are polynomial growth. What's nice is we no longer have x near 0, so we don't have to worry about these blowing up. X is greater than 0, well behaved. This has exponential decay. And so because this has exponential decay, this is much less than e to the negative pi x if x is big. This has exponential decay. This integral is going to converge for all values of s. And this gives me a definition of the Riemann zeta function that will work for all values of x. So all values of s. And that's the key idea of this proof of the functional equation of the Riemann zeta function. We have this integral representation that makes sense for all values of s because now I've stayed away from s equals 0. Going up to large values of x is no problem. So no matter what s you give me, this is fine. This is going to grow at most polynomially. This decays exponentially. All right. This is a good place to stop. And so we will continue with stuff like this next Monday.